Okay, so this was sort of a result that we showed that the excess risk over a class of functions for the empirical risk minimizer h hat n is controlled by this supremo, this deviation, where this LH is sort of, recall LH, let's say Z is just L of HX, and Y, something like that. And so if you define this loss function class, then you can see that the excess risk is bounded by the supremo of this deviation. So this is the empirical average, and this is the expected population average. And so then we focused on trying to control a quantity like this. And so we introduced some sort of terminology, the terminology of empirical processes. So, so this is the empirical measure associated with a sequence of training data. And then we had an IID, or Rademacher sequence, independent of Z. And this is the corresponding, let's say, Rademacher measure, where you put a sign at each location Zi, like random sign. So epsilon I is independent of Zi. And also introduce this notation. So taking the integral of a function against the measure, this is a simple notation. So if you take the integral of f against this, you basically compute the average of, so that's sort of the basically integral of f against pz. And this is the integral of f against p. Okay, so these are all the same because they're IID. And so we can see that the quantity that we want to control is basically supremum over f in f. And then this form is bilinear, so I can just verify that I can sort of do this. So this is suggestive of like an inner product. It's not an inner product, but the notation helps sort of both the notation and sort of conceptually connects it to inner products. So we want to control this. The first idea was to relate this to the supremum of the other process, so supremum over f. F and this symmetrized version, basically. So this is the Rademacher process, supremum of the, this is the empirical process. The empirical process is basically this guy. So f maps to this. It's a random process. So each coordinate is a random variable, but the coordinates are indexed by functions. So the index set could be like an infinite, uncountable set. And the Rademacher process is this corresponding process. And you can see, again, this deviation is just that. And then we wanted to relate this guy to this guy, okay? And the idea was to use symmetrization. So we went through some sort of like a progressively more complicated argument. But the basic idea is that you just, if you have a distribution centered around the mean, so you want to get rid of the mean. So you want to basically center it around 0, and you just care about the basically deviation around the mean. So you can sort of get rid of the expectation here. So this is the expectation, basically get rid of this. And the point was, not going to repeat this, but the point was in the end, we had a result like this, that the expectation of the supremum, or the expectation over Z, is bounded by twice the expectation of this supremum of this Rademacher process, where now the expectation is both under Z and epsilon. Okay, and then that's the symmetrization argument. And at this point, we started to talk about now how to actually control this. Okay, and last time we started doing some calculations. So if you, yeah, so it was around here that I sort of we got stuck. Do you guys remember sort of the issue that we had? So do you guys have any chance to think about it? Yeah. Oh, okay. Right. Okay. So that's good. So okay, let me maybe back up. Yeah. What should I do? Let me go to the other slides because I added something here. That's basically the idea. There's sort of the issue with the absolute values and the other issues. But let me try to. So that's the new version that I have. I just removed the z and epsilon that I had there. It's just when I don't put z and epsilon here, it's just expectation with all the randomness. Okay, so we want to control. This is just expectation, respect to z and epsilon. So what we want to control is. And okay. So we now want to control expectation p z epsilon f, and so I can do it with iterated expectation. So expectation over z and expectation over epsilon because they're independent. This is like Fubini. So I'm going to do this, right? And then I'm going to control this separately first. So in this case, you can think of it as conditioning on z if you want. So you condition on z, z is fixed. Now I just take the expectation with respect to epsilon. So if I unpack this, this is just expectation over epsilon of, if you recall, this is supremum, f in f, absolute value 1 over n summation epsilon I, f z I. That's the meaning of that notation. Okay. So there is some notation that I want to introduce, which will simplify. So that's the object that we care about. So just have a look at this. Let me introduce notation and we'll come back to this. Okay, so what I want to introduce is this Rademacher complexity of a set in Rn. So if you imagine, I'm going to use the notation that I had before is like f z. I'm going to also write it as FOZ. This matches some other notation, some other book, like the book by Ben David. And yeah, so the this notation is the set of all functions, basically restricted to the training set. Okay, that's the notation that I used, and then this is the new notation. I'm going to use f in f. Okay, so this is going to be a subset in Rn, right? So if you imagine this can be written as 1 over n expectation over epsilon. I can say supremum over t in FOZ. Absolute value summation I from 1 to n epsilon I ti. So t is a vector in Rn. Okay, so as f varies, little f varies in capital F, you can think of this as so this would be some vector t in Rn. And so what I'm doing is basically I do a change of variable. Okay, so as long as t varies in this sort of traces all possible like vectors like that, and so the supremum is exactly that. So this simplifies. So the complexity of the f here is moved into the index set, and this quantity here we can denote as the Rademacher complexity of FOZ. Okay. Right, or you can write it as an alternative thing is to just write it like that. I think I have it in the slides like that. So this would be I could do supremum over t in 1 over n FOZ. It's just the rescaled version of this. It's just these are equivalent. So this would be, again, by the notation that we're going to introduce. This is going to be FOZ over n. So it's just, this is a subset of Rn. Either you rescale, you're rescaling the set just comes out because of the linearity you see. So that's the notation I'm going to use, and then you're going to focus on quantities like this first to understand these quantities better. Does this make sense? Right, so with this notation that I have here, that's the Rademacher complexity. So if you have a subset T in Rn, the Rademacher complexity is defined as the expectation of the supremum of this quantity, which is just supremum of this. So T varies in T. This is a vector in Rn. Epsilon is a Rademacher sequence, or a sequence of independent Rademacher variables. So this is a measure of the size of the set. Yeah, maybe later I'll give you some geometric idea. So this is like if you maximize a linear function, right, over a set. So there is a normal to this linear. So the level says that this function would be orthogonal to epsilon. And then so you vary it. And the maximum you hit sort of a certain point where, so you're looking at all the values of the t's that are in T. So if this is T, you move this until you like the last touch this, and that would be the value of this. And you can also show that this is I believe it's going to be equivalent to, maybe show this, that this is equivalent to 1/2 expected supremum T and S in T epsilon T minus S, something like that. Okay. So you can separate the supremum. And so with this, it would be, if you imagine it, it's just, you're measuring the, basically the difference between these two. So this is the smallest that it can get. This is the largest that it can get. So it's like you're looking at the difference. So you're measuring the width of this set in that direction. Think a little bit about this. So this formulation, so like it's half this width basically. And then the expectation is just you vary this vector randomly. So it's a random direction in Rn. And so you measure the width in different directions. The same idea can be used to measure the width using the Gaussian vector. So if this epsilon is replaced with a Gaussian, standard Gaussian vector, canonical Gaussian vector, then it will be called the Gaussian width. So you can call it Rademacher width if you want. Yeah, just think a little bit about this formulation. This is just measuring the width in both directions, basically. The size of the set between the two slabs. Okay, so that has a nice idea of an average width of the set, and so it measures how big the set is on average. So some basic properties, if you, so this doesn't have an absolute value. So without the absolute value, it's an interesting quantity because if I shift it, it doesn't change. Okay, so it makes sense because if you might have a measure of size, you don't want it to change as you shift things around. As you can see, if I just basically this notation is just hopefully this is the set of all points that look like this T0 plus alpha T, where So you rescale the set and then shift it. And so if you plug this in here, you can see epsilon T naught comes out of the supremum, and the expectation is 0 because the epsilons are 0 mean. So just verify for yourself. And then alpha, if alpha is negative, you can absorb the sum into this. The absolute value comes out, doesn't change the supremum. So verify this for yourself. This is a nice property. It tells you it has the properties of a size. Okay, so if I rescale the set like by 2 or -2, it just multiplies by 2. And if I shift it, so intuitive property of any measure of the size of a set, sort of, you know. And then I'm going to define the version with the absolute value as our ADST, let's say. And then you can show or argue that this is equal to the Rademacher complexity of T union -T. So you flip T around the origin and then take the union. So why this is true? Online people can also chip in. Yeah, okay, good. So yeah, so this like absolute value of x can be written as like maximum of x and -x, right? So I can just, instead of taking the supremum over the absolute value, I can take supremum over both t and -t of this without the absolute value. So just think a little bit about this. This is so you can see this is not sort of symmetric. This if I have some sort of there's a bit of a problem here. So if you have some set here, right, small, but it's not centered around the origin, if I take the Rademacher complexity, I measure the width of this property because I just move it around, it doesn't matter. But if I look at the, so let me do this, it's like something like that. If I do the absolute value version, I'm gonna just have to reflect it here. That would be -t, right? That's t. And then the average width would be like something huge, right? So this with the absolute value is really not, it's actually should be like a, let's call this like, the average width is still like, there are cases where it's small, but there's also like cases where, so you see the diameter is big, and then the average width is big. Just, it's unfortunate. So if T is symmetric, then things are good. So if T is symmetric, both are the same. Right? This and this would be the same. Symmetry means T is equal to -T. Okay, so question. Yeah, so it measures the, so if I look at this quantity, supremum epsilon T minus S over T and S, this measures the width in the direction of epsilon. Okay, so you maximize epsilon T basically, and you minimize epsilon S, right? So in this direction, the maximum would be this. The maximum achieves at that point, and the minimum achieves in this point, because sort of in the direction of epsilon, these level sets increase. So the value, so as I increase so what I'm looking here is the level sets of things like the set of all t such that epsilon t is equal to c. Call this level set c. So the level sets sort of move in this direction. So as I increase c, these level sets are orthogonal to the direction of epsilon. So you think of the direction epsilon. And as I move c, I like increase c, I'm like increasing this. And so what this is doing, this is like the supremum epsilon t in t, and this is the infimum, basically. Epsilon, let's say s in t. And so the difference is like half the difference would be the Rademacher complexity. Okay, makes sense? Yeah, okay, good. Any other questions? Okay, so these are some basic properties. There are other properties. So for example, I'm going to sign it as a Hort problem. The other property is that like Rademacher complexity of T is the same as the Rademacher complexity of the convex hull of T. And this follows from a basic result that if you maximize the convex function over a set, it's like maximizing over the convex hull. And you can also see from this, if just imagine if a set is like that, these slabs are not going to see they just see the convex hull, basically. You don't see the non-convexity, right? Just measuring the width is the same as if I just look at the convex hull. Geometrically, it's clear. So there are other properties as well. So we'll see. So these Rademacher quantities have interesting properties. So now back to the setting. So if FOZ is this setting, just a comment that this notation makes sense because these people think about the Z as a function. So you can think of Z vector as function mapping n to Z, okay? So if you give me I, I'm going to output ZI. This is like the script Z. And so this is a function that maps indices to numbers. And then this is a function that maps numbers to, like Z's to, no, not numbers. So mapping index to this, and then composition with F, you map this to reals. That's sort of the F of Zi. So we are composing basically this function and this function. So that's the good notation. In any case, this is the like the restriction of F to this set Z. That's a subset of Rn. And as we saw, the RADS, by the definition of this subset of Rn is just the Rademacher complexity of, sorry, this is the absolute version of the Rademacher complexity. There's this quantity, and also it's the expectation over epsilon of this supremum of the Rademacher process. And then if I take another expectation on both sides, this side depends on Z, take the expectation on about like in terms of Z, I take another expectation here in terms of Z, you can see basically I'm having this expectation sort of. So the expectation of this over both epsilon and Z is the expectation of the Rademacher quantity over Z. Okay, that's the quantity that bounds the expectation of the empirical process. Okay, this is just some notation. Okay, so back to again this basic lemma that we had, the same lemma. This side I can write again as twice. So the two I'm multiplying by both sides. So this supremum is the supremum of the empirical process here, and the F is the loss function class. That's just a rewriting of this bound that we had on the excess risk. And now I have a bound on this empirical process, which is bounded by twice the Rademacher process. So I get this result. So I get 4 times the Rademacher process. And then the expectation basically of the supremum of the Rademacher process. And then this is like 4 times the expectation of this Rademacher complexity. Okay, so that's the result. Just a bunch of more notations. The main point is that this follows from the basic inequality, and the second inequality follows from symmetrization. This is like basic inequality followed by symmetrization gives you this. This is just the definition, sort of, almost. Okay, so just keep this in mind. Now we're going to control the Rademacher complexity. So if you look at the high-dimensional probability book, for the Gaussian version, they call this the Gaussian width, and this one, they got the Gaussian complexity. So it might be better to call this like Rademacher complexity, this the Rademacher width, if you want to make it make the distinction. I'm just going to be very sloppy. Just have to. I mean, from the context, it should be clear. So the naive bound, now let's try to bound this. So if I have a Rademacher complexity RT, this is without absolute value, is always bounded by the RABST. And this is just this. By definition, the last time the naive bound that we did was the Cauchy-Schwarz. So if you do the naive bound, you would bound this by the norm of epsilon times the norm of t. And the norm of epsilon is like root n, because they're plus minus ones. And so you get this bound, root n times sup. This is like the radius, like half the diameter of the set. This is a valid bound, but this is not in general a good bound. So this is the better bound using the concentration ideas. So if you have a finite set of size n, a subset RD, and if you take the t bar to be like the, let's say the average, any basically shift you want, basically. And then you look at the deviation of t from this average, or any fixed point, basically, in the set, all this row, then the Rademacher complexity, or the Rademacher width of t is rho times root 2 log n. So it's logarithmic in the number of points. So that's the main result that we want to use. Now again, this is, just to remind you, this is expectation over epsilon sup t in t epsilon t. Okay, that's the idea. So how do we prove something like this? Let me give you a hint. So if you recall, or hopefully you have you seen Subgaussian? Anyways, okay. So we recall, this is one definition. If a zero mean random variable x satisfy this MGF inequality, is Subgaussian. So the MGF of x is uniformly controlled by the MGF of a Gaussian, and then sigma is called the parameter, Subgaussian parameter. So the first result, this is a very important result for Subgaussian variables. If you have a zero, like a sequence n, sequence of size n, of zero mean random variables, there's Subgaussian parameter sigma. So not necessarily independent. So they need not be independent. Then the expectation of the maximum is root twice sigma squared log n. Okay, so it scales with root log n of the number. Rather grows slowly. There's a high probability version as well that you can prove. But this expectation, there's a nice way of proving it. So this is the hint. So Jensen's inequality on e to the lambda z, where z is the maximum exercise. Can you fill the details maybe? How should we prove this? Just want to do it so that you remember this argument. So max is a convex function. Okay, so expectation of z, and then the expectation of, let's call it e to the expectation of z. Actually, you're not going to use the, so we're going to use the fact that e to something is also convex. Okay, so which way the inequality goes? It should be this way. So if you pull out the expectation outside a convex function, it gets bigger. Okay, so that's the Jensen's inequality. This is what? Expectation. I'm going to do a lambda here as well. I'm going to allow a parameter e to the lambda. just in case. So lambda is bigger than or equal to 0. Then this is e to the lambda maximum of xi, right? And then I can bound this by e to the lambda summation xi. That's sort of a bad bound, but it works. Oh, actually, I'm going to do something like this, I believe. Would this work? Okay. This is better because they're non-negative, right? So e to the lambda, it's like e to the lambda x1, e to the lambda x2. You're looking at, this is like the maximum. You want to do it. This is equal to e to the maximum, e to the lambda xi, right? This is because of the monotonicity of, and then we get that. Okay, now this is bounded by summation I e to the lambda xi. Now we're going to use the Subgaussian inequality, right? So this would be bounded by e to the lambda squared sigma squared over 2. So this is bounded by what? N times e to the sigma squared over 2, right? So what is the next step? Say step 1, step 2. Yeah, good idea. Take the log, we get log n plus lambda squared sigma squared over 2. Or I get ez, that's the quantity I want, log n divided by lambda plus lambda sigma squared over 2. Right, now I have a bound, this is like not equal, like bigger than or equal to. I have a bound parameterized by lambda. What should we do? Optimize, yeah, so try to minimize this. And usually in these cases, the minimum happens if you set the two equal. Right? So if I let, so optimal lambda satisfies log n lambda. You can take the derivative set equal to 0. Gives you the same thing. So what I would get is lambda squared is what? 2 log n divided by sigma squared. Right? It says lambda is root 2 log n over sigma squared. And so the bound is e. See, the two terms are equal by construction. So I get log twice log n divided by root log n divided by 2 sigma squares. Let's see if it works. So I get 2 root 2 sigma squared log n. Did I have an extra 2 here? Oh, yeah, 2 is the other side. So root 2 log n over sigma squared, it works. Okay, so one of the 2's cancel out. So you get this nice result. It's also good to remember the 2. It's just a very sharp result, root 2 sigma squared log n. So it's a very interesting argument, gives you a nice bound. You imagine this is a bad step, but it works and gives you a nice bound actually. Okay. So how do we now prove this? So that you need some sort of an, so this is like expectation of, this is like the maximum bunch of Subgaussian. So if you have a, so the Rademacher variables are Subgaussian, okay, and then this inner product, because it's a linear combination of independent Subgaussian random variables, is still Subgaussian. They're not independent of each other, these quantities for different t, but we don't need that. So we just have this nice result. The only thing is that how do I compute the Subgaussian? So epsilon i's are IID Rademacher. From this, it follows that this guy, which is summation epsilon I ti, this is going to be Subgaussian as well. So because Rademacher is Subgaussian. So what is a good Subgaussian standard for? Let's call this sigma epsilon I. Sorry? 1, yeah. So for Rademacher variables, it's 1. It's just easy to show. It's like e to the lambda epsilon I. This is going to be 1/2 e to the lambda plus e to the negative lambda, which is cosine hyperbolic lambda. And then you show that this is bounded by lambda squared over 2. This is a nice inequality. Just do, for example, Taylor expansion if you want. Say a little thing here. It's not hard to show that. So how do I control the Subgaussian norm of, let's call this sigma t, would be Subgaussian norm of this quantity. Do you remember the properties of Subgaussian variables? Sorry, this is like sigma t is equal to the Subgaussian norm of epsilon t. How do I control this? Okay, yeah, so because they're independent, it's just going to be the square of this basically is going to be bounded by the square of Subgaussian norms of these. And this is just going to be like ti squared Subgaussian norm of epsilon I, which is 1. Okay, so sigma t is basically norm, bounded by norm t. The square is bounded by the L2 norm. So individual ones are bounded by this, and then this is further bounded by rho. So there's a little argument here that I can, without loss of generality, assume that this t bar is 0. Why? Maybe. Yeah, so it's invariant to shift. So I can just shift it to t bar. And so rho would be the maximum norm of t in that case. So that's bounded by rho. So now if you plug in everything there, so that would be the result. So it's like 2 rho squared log n, and this capital N. So that follows from. So it's a combination of the result for maximum of Subgaussian variables and the fact that the sum of independent Subgaussian variables is again Subgaussian, and then the Rademacher is Subgaussian. So we have that nice result. Okay. So this rho is sort of like a radius or diameter. So if you think of that's reasonable. So if you have like a set like that, then you can see from the argument that we did, we can put any t naught here. So you can center it around any points. But this is sort of the minimizing this sort of. It's actually not clear that this minimizes it. So if you look at it, like the book by Ben David, you can define it to be like rho being min over t naught, max over t and t minus t naught. So the smallest that this can be. Like center it around a point, and then the maximum. If this was like the L2 norm, there would be the T bar. In any case, so you set it in like at some point, and then just measures the like a radius type thing, and that's reasonable. That's there, and then you just pay the price, which is the size of the set in logarithmic fashion. Sounds good? Like everyone happy? Now, okay. So how can I use this to control? That's the proof. Okay, so now let's back up. So we went down this road because we wanted to give a rigorous proof of the result in the case of finite VC dimension. So now I have this quantity, and I'm going to relate it using this to the size of this, and the size of this is well behaved if I have a finite VC dimension class. So let F be a Boolean class. This is the result that we showed of functions on an endpoint set x, let's say z in this case. That's our sort of set z. And the VC dimension is nu. Then Saur Shalah says that then the size of f is controlled by this, like n over nu, e n over nu to the nu. So it's like polynomial in n. So now suppose f is, I'm going to assume that f is symmetric for simplicity. VC class, so VC dimension is nu, and f is one bounded, can be like p bounded without any issues. So then the cardinality of this set, this is just the restriction of f to the endpoint set z1 up to zn by that lemma is the cardinality e n divided by nu to the nu, right? And so if I apply our result, so if you take t to be this set, you have the cardinality and also have to control the diameter. Just because we're symmetric, let's say center at 0, so supremum t squared is, just remember that this is like t would be equivalent to like 1 over n fz1 up to fzn. That's the change of variable that we're doing. So the norm of t would be just 1 over n squared times this squared, sum of these squared, and then these are bounded by 1, so I get n divided by n squared, so I get 1 over n. So because we are symmetric, the absolute value here is the same as the usual Rademacher Rit, let's say. And so this would be bounded by root 2 times the supremum, which is 1 over n, right? And then the cardinality of the set, FO z over n, log of this, sorry. Log of this guy. And so if you expand, it would be like root 2 nu. It's just going to be this. Okay. So plug this in here, and take the log. You get that result. Okay. So this is nice because it's saying that the Rademacher complexity of this function class grows like with the dimension nu, like the VC dimension. There's a log factor, so log n over n. This one actually we can remove, and we talk about this. With a little better sort of argument, we can do like nu over root nu over n actually. But let's say this is not bad, nu log n over n basically. So this case like roughly scales like root nu log n over n. So it's going to 0 as n goes to infinity. And if you recall this, now I can take the expectation of both sides over z. This side doesn't depend on z, right? If I take the expectation over z, I have the same bound. And so if you go back to the result that we had, so the expected excess risk now is controlled by the 4 times the Rademacher process. That's sort of basically this. And so I get this result. That if I have an empirical risk minimizer and let's say f is a class of functions that contains So I can always make f bigger, get an upper bound. So there is like a symmetric one-bounded function class that contains the loss class. And then, for example, this is not symmetric, and symmetrize it, call it f. And the VC dimension is new, then we have this result. So this is like a bound in expectation. So this is saying, so this expectation is with respect to z. So this side, the loss, if you remember, this excess loss is generalization error. So there is some sort of an expectation in defining it on the test point. But this is a deterministic quantity when you apply it to any function. Now this is random because of the randomness in this. The randomness in this is because of the training. So training goes into the empirical loss. So this is LNH is just 1 over n summation. LHXI and YI are 1 over n summation. LH ZI are from 1 to n. So we take the expectation over the training. This is like saying, on average, the excess loss is controlled by this, and you can see it goes to 0 as it goes to infinity. So you can sort of consistently learn finite AC classes. Okay. You can turn it into like a high probability inequality by using the Markov inequality. So this is a version of the Markov inequality. So if I basically divide this expectation by delta, let's say this is non-negative. The probability that this is bounded by this quantity divided by delta is at least 1 minus delta. You can use that. So what if I divide by 1 over delta, the probability that this is bounded by 1 over delta times this is at this, so you can say epsilon h. This is bounded by 1 over delta root 32 nu log e n divided by nu with probability at least 1 minus delta. But you can do better than this. So this is like bound. So as I make delta small, this blows up like 1 over delta. I can make this logarithmic in log 1 over delta if you use the exponential concentration. Okay. So if you don't have any questions, I want to talk a little bit about that. Okay. Questions? Online questions? Okay, so how do we turn it into a high probability bound proper dependence on delta? So this is the concentration result that we're going to use. So for any B uniformly bounded class of functions f, we have this concentration. So the supremo, the empirical process is bounded by twice. That's basically the bounded that we had. So this is like, we're saying PZ basically minus PF is bounded by expectation of this guy plus alpha. And then by the symmetrization argument that we did, this is further bounded by twice expectation of PZ epsilon. So that's the symmetrization argument. Symmetrization. And so this result is basically saying this minus the expectation is bounded by alpha. So it's a concentration result for the supremo of the empirical process near its mean. So half of it we showed the symmetrization. The only thing I need to show is this concentration. I want to show that this is at least 1 minus e to the negative n alpha squared 2b squared. Okay. And this one follows from the so-called bounded difference inequality. Have you guys seen bounded difference? No. Online people, have you seen bounded difference inequality? So I usually talk about this in 200C, right? So let me remind you, F satisfies the bounded difference property with constant Ci. This means something like this. So if I have a function, these functions, if the function takes n coordinates, so think of this as the training data. If I flip one coordinate, keeping all the others the same, so I'm flipping zi to z prime I, and then take the absolute value of the difference, we want it to be bounded by some constant ci, irrespective of the values of the arguments. So as long as these are in the domain, so z1 up to zn, and also z prime I. They vary, they could be anything in, let's say, script z, and I want to have this uniform bound. So this is called a bounded difference property. And if I have a function like this, basically the idea is that the function doesn't change much if I change a single coordinate at a time. There's not like huge difference. It's just the difference is controlled, bounded, not unbounded. And then you have this concentration result. So if you have random variables, the i's, these could be defined in a very abstract space. They're independent, the coordinates are independent. Then if I apply the function to z minus the expectation of the function, this is going to be like controlled by this. Okay. This is like a Hofstein bound. If you imagine, for example, if I have fz1 up to zn, let's say that is, I could do, let's say, average if you want. That gives you the classical Hofstein bound. So this has the bounded difference property, let's say, dp, with ci equal what? So if I change one coordinate, this should be zi. Assuming that zi's are bounded. If the zi's are bounded, to b over n. Yeah. So if you change one, it's just the difference would be like 1 over n, absolute value of zi minus zi prime, 2b divided by n. And so you plug this in here. So this bound would be, so probability dot less than 2e to the negative 2 alpha squared divided by 2b over n squared times n, because the sum, there's sum of n of them. All right, so you get 2x negative n what? Alpha squared over 2b squared, which is the Hofstein bound, like modular constant. But you could also do like zi and ai and bi. You get the Hofstein bound. So it's a strict generalization of the Hofstein bound. Two more general functions. I've put this as an exercise. You can now show that if f is b bounded, then this process, like the function that takes z, maps it to the supreme of the process, empirical process. This is also has the bounded difference with exactly the same like constants, 2b over n. Should I? Do you want to do it as an exercise, or? Yeah, just do it as an exercise. I'll try to assign it. It's not hard. And so if that's the case, then I have my concentration. Okay, so I have this concentration with exactly this quantity, because the calculation that I did here is exactly the calculation that you do here. And so that's going to be the, so we have proved something like this. So because this has bounded difference property with ci 2b over n, that would be the probability. Okay, so just saying the probability that this is like f of z. F is a bad notation. I should have like say G of Z, for example. So this is like G of Z. This is expectation. G of Z. And so that's the bounded difference property. It holds, like, if you remove the absolute values, you can also remove the 2 here. So that's what we're doing. Okay, so I have this result. And so, so in the case of, so let's see what happens here. So if you use bounded difference inequality, we get with probability bigger than 1 minus e to the negative n alpha squared over 2b squared. I'm going to assume the b is 1. So 1 bounded loss. I would have the probability that with this probability, this guy is bounded by twice pz minus p, which is bounded by twice expectation of pz minus p, plus alpha is bounded by 4 expectation of pz epsilon. It's like that, and then plus 2 alpha, something like this. So this is bounded by the expectation plus alpha. There's a 2 here. I get, and this is bounded further by 2 times this. I get 4 plus 2 alpha. And this is bounded by root. Yeah, 32 is like, because I have a 4 here, move the 4 inside. Okay, I forgot to mention that. You get 32. So you get root 32 nu log n en divided by nu divided by n plus 2 alpha. Now I want this part to be delta. So let this be delta, right? So what I would get is n alpha squared over 2 is 1 over delta. N alpha squared over 2 is log 1 over delta. And so alpha is root 2 over n log 1 over delta. Okay, if I plug in here, I would get root 8 over n log 1 over delta. You can see the dependence on delta is log 1 over delta. Okay, and this is going to be delta. So the result that we get is that the excess risk with probability like 1 minus delta is bounded by this plus root 8 log 1 over delta over n. So this is quite a nice result. That's what we have here. Okay, so that's basically the end result, sort of, for the VC dimension. So if the loss is 1 bounded, symmetric, VC dimension nu, then I have this result with high probability, which is quite nice. A couple of things that we can do is that this you remember, this comes from bounding the expectation of the Rademacher complexity, or the Rademacher complexity itself. This part can be removed, sort of. I want to maybe talk about this at some point. And the other thing that you can do, so that's the proof that we did just now. You can remove the symmetry assumption. So if you go back to how we did this, you can actually, instead of let's say this guy appearing, which is basically the Yeah, so this guy, or basically the absolute value of the Rademacher process appearing, you can have just the Rademacher complexity without the absolute values. Then you don't need the symmetry. And then just to hint, maybe I'll assign this as a homework problem as well. If you go way back, the way we did this was here, the basic inequality argument. If you look at this, that's the step that so this is the population loss of H hat minus the best in class, and then we added a subtype L hat n. So you can see if I bounded both of these by the absolute value of this supremum. Okay, what I can do is that I can bound this by supremum over f, or say h in h of LH minus L hat NH. There's no absolute value here, okay? And then this term, because it's evaluating things at a single function, this can be controlled by the usual Hofstein, because there's no, so the issue with this term was that I'm evaluating something which is random at a random function. It depends on it. So this is hard to deal with. So we bound this by the supremum. This one we can bound by using just the Hofstein if the L is bounded. So if you go through this, everything sort of works out in terms of the supremum, and the supremum is like the one-sided Rademacher. So you can get things done. It's just easier. So you have to go through the symmetrization argument. That would work. All the other things, and so the symmetry is really not an issue. So we could, it's simpler to write these because otherwise I had to add another term. Yeah, so this one can be removed. And then one last point is, because we are looking at the loss class, we're looking at the VC dimension. You can show that the VC dimension, so I can take F to be exactly this, okay? Because I don't need symmetry, I just take F to be this. And then the VC dimension of F, which is that, is bounded by the VC dimension of H. So can you argue that maybe? Or maybe this is an exercise. So this is like the functions that look like this. Okay, so we're saying that the VC dimension of this class of functions is bounded by the VC dimension of class H. Argument. Yeah, so basically if you look at like the collection of functions that you get, so how many different kind of points I can get like this, like fix a set of xi's and yi's, the number of different things that I can get here, the only thing that varies here is h. So if h of these xi's are the same, then this would be the same. So the different, like the number of different like patterns that I can get is at most controlled by the number of different patterns I can get by the collection of h's. So intuitive, we can also write it formally. So you assume that, for example, this is bigger than nu, then show that it has to be bigger than nu. Or this is equal to nu, then this has to be bigger than or equal to nu. So this is nice because you just don't have to worry about the loss class. It could be smaller, like the loss could be like constant everywhere. So, but generally speaking, if this is not that loose, then you can just worry about the VC dimension. So basically, you could do the classification with VC dimension, with finite VC dimension classes works. Basically, that's the result. Okay, so you could do empirical risk minimizer or any class of functions H for which the VC dimension is finite, then you'd have this result. Questions? Comments? I have a couple more points here. Not sure which one I want to say first. There's one last piece from the VC dimension business that I want to talk about, which is the connection of the VC dimension with dimension. Maybe I'll talk about this, and then next time talk a little bit about how you can remove the log. That requires metric entropy ideas. And then we have sort of a complete picture, sort of. Then we change gear a little bit. So the nice thing is, so we have the VC dimension, and then we have the algebraic dimension. So the algebraic dimension, you know, like if you have a vector space, there's a dimension, okay? And one question is that are these guys related? There's a nice relation if your function class, let's say I have a function class G, it's a vector space of functions, which is often the case. You have like L2 or like C infinity, like C, let's say continuous functions. These are vectors. Functions are like when you add them or scale them by a constant, they're still functions. And if the class is closed under that, that would be vector space of functions. Let's say the dimension is finite. Then consider all the sublevel sets of G from this class. So as I vary G here in this class, these are sublevel sets. So the sublevel sets define a collection of sets, and we can define VC dimension for classes of sets. There's like a bijection, like equivalence between functions, indicator functions, and sets. So when I say the VC dimension of this class of set, I mean the VC dimension of the function class, which is the indicators of these sets. Okay, so the VC dimension of the indicators of the above sublevel sets is controlled by the dimension of G. Okay, so this gives you a nice connection. So how do we show this? I need to show that. So in order to show that the VC dimension is at most something, you have to show that no more than, so if I add this +1, there's no set of points that can be shattered with that many points. So pick a subset x1 up to xn. So like I'm using x here. These are, let's say, z if you want, but just forget about just so we're talking about just a class of functions. So x1 up to xn subset x, and then define the linear map. It's just the one that just restricts the function g to this set. Right, so that's the notation that we used before. So the first thing to note is that the dimension of phi of g is less than the dimension of g. Right, so so phi of g. So this is the right. So phi of g is just phi g as g varies in g, right? The range of this map, right? So because this is a linear space, vector space is a linear map. Phi is a linear map. You imagine this is with a linear subspace. Okay, so this is a linear subspace. So linear map, yeah, I have it there. So linear subspace of G. G itself is a vector space. It's a linear subspace, and the dimension would be at most dimension of G. This is sort of simple. So if you have a linear function, dimension of the image cannot be bigger than dimension of the input space. Okay, and dimension of G by assumption is n-1, which is strictly less than n. So if that's the case, then there exists a non-zero vector such that this multiplied by anything in the range is 0. Why is that? Yeah, so this has like a it's like it's a null space of the transpose, basically, right? But you can imagine if you have a subspace which is, you can do it that way, right? There's a relation between the kernel of this phi transpose, this map transpose and the range. But like intuitively it's clear because I have, let's say if I have in R2, there is a subset which is dimension is less than R2, there's always a direction that I can find that's orthogonal, right? Because there's one dimension is less than this, there should be a direction that's orthogonal to everything. So there's this thing. Now assume that that's collection of sets, the sublevel sets shatters the set of points. This is like a generic set of points. Then there exists a G such that the sign of Gi is equal to the sign of this Vi. So why is that the case? So recall the sublevel sets are these, right? So what this is saying is, if I shatter the set of points, I can get any patterns, any sign patterns for these G's, right? So what it's saying, like if I shatter, if SG shatters x1 up to xn, we can have any sign patterns for GXIs, right? Because it's saying, think of the indicator 1 or 0. If it's 1, it's like negative. It's 0, it's positive. And so it's saying all possible things are possible. So I can generate, like, I can reconstruct any sign pattern. So basically there exists a G that whose sign pattern is given, like, reproduces the sign pattern of this vector that I have. You can also define the sign of Z to be -1. And without less of generality, let's say assume one of these VIs is bigger than 0. You can argue why that is. And so the sign of, like, so Vj is 1, and then Gx is also bigger than 0 because of this. For that G, then this side is true because this holds for any G. And then this is just the inner, like you can see, this is like the, sorry, it's just summation Vi GXI, and these have the same sign, okay? By definition, so this would be absolute value this times absolute value, this bigger than absolute value this times that, and this is bigger than 0. Okay, so this contradicts that this has to be 0. There's a contradiction, so there can't be any set that can be shattered. Okay, just think about this a little bit. So this proves the result, and then you can use this result to show interesting things. So for example, a lot of sets, so for example, the set of linear half spaces, or the set of like spheres, or more complicated things, these are like sublevel sets of linear classes of functions. We'll come back talk about this a little bit later. But then you can get interesting, so immediate bounds on the VC dimension. Okay. Questions? Okay, thank you guys. Then see you next time.